All right, let's go ahead and get started. I do want to welcome you to this worksheet. This is potential energy in a reaction, and we're going to start with this diagram here. This is a potential energy diagram. What do we mean by potential energy? Well, we mean essentially energy that is held in bonds. So every chemical, every molecule has within its bonds energy that we call potential energy. That energy over the course of a chemical reaction is released. So if we begin on the left-hand side of this diagram with reactants and we look from left to right, this is the reaction progress as we go from left to right, going from reactants to products. And what we see is that if the potential energy of the reaction overall begins at some level, then it requires some amount of energy, and we'll talk about what that energy is called, to increase. So the potential energy must increase initially and then it falls back down to a lower level, a level lower than what it began at. So this is essentially a potential energy diagram for a type of reaction called an exothermic reaction. So let's talk a little bit about exothermic versus endothermic reactions. What do we mean by an exothermic reaction? Essentially what we mean is reactions that release heat. Okay, so if the energy of the reaction releases heat, if heat is a product, we call that exothermic. That is an exothermic reaction. If, on the other hand, it requires heat to make the reaction proceed, we call that endothermic. We can think of energy in this, or heat in that example, the endothermic example, as being a reactant, all right? So let's talk a little bit about the diagram itself. What do we mean by a reaction? Let's take a look at this reaction. It says write the balanced equation for the reaction as described in the paragraph above and graph above. So they ask us to react nitrogen dioxide, or NO2, with carbon monoxide. And when we do that, we get nitrogen monoxide and carbon dioxide. It's a 1-to-1 to 1-to-1, mole to mole to mole relationship. And so that's the balanced reaction that we're looking for. Now they asked the question, if this reaction was reversed, how would the reaction look? So this reaction is reversible. It can go either way. So reactants can go to products, but products can come together to form reactants. If they do, we simply reverse the reactants and the products. So now the previous products become reactants and the previous reactants become products. And this is the reversed reaction now. So that's the reverse reaction. So on number 3, it says, on the graph's lines, label the following. They're asking us to label the potential energy of the reactants, the potential energy of the products, the activated complex, and the activation energy and the energy change, which we call delta H. So let's look at those. So here's the potential energy that we were looking at, but this time with those things labeled. On the left-hand side of the potential energy diagram, we see potential energy of the reactant. So this is where the potential energy of the reaction began. So this is the amount of energy that was contained in the bonds to begin with. Now it requires some initial amount of energy to get the reaction going, to destabilize the bonds so that they can be rearranged into new bonds. And we call that the energy of activation. It's sometimes abbreviated E sub A. So the energy of activation is the energy to go from where we started from up to something, the apex of this diagram, called the activated complex. Now the activated complex is kind of an intermediate between the reactants and the products. And the activated complex is a high energy, relatively high energy complex, but it requires energy to get there. Once we get there, then the reaction can proceed to completion. And that's what's happening as we move down on the right-hand side. So on the left, upper left, we have potential energy of the reactants. In the lower right, we have the potential energy of the products. The difference in energy between the reactants and the products we call the enthalpy change, or delta H. Delta H, all right? So that difference between the initial energy and the final energy, however large the energy of activation must have been, the delta H is that difference. If we are dealing with an exothermic reaction, and we are dealing with an exothermic reaction in this case because the potential energy of the products is lower than the potential energy of the reactants. That means some of the energy was released, then the delta H is negative. It's a negative number. If we had been dealing with, on the other hand, a reaction in which the potential energy of the products was higher than the potential energy of the reactants. That would have been a positive delta H, known as an endothermic reaction. All right? So let's go on to the next one. It says is the forward reaction represented in the graph endothermic or exothermic? Justify your choice. Well, I think we've answered that now because we've said that because on the graph, because of the fact that the potential energy of the products is lower than the potential energy of the reactants, this would be an exothermic process as shown. This is going to be a release of energy, an exothermic process as shown. So the forward reaction shown is exothermic because energy is released. And we're done with number 4. Let's look at number 5. It says, what is the number of kilojoules that were stored in the bonds of the reactants? And we're going to say about 80 kilojoules. How do we arrive at that? Well, the way we're going to do that is we're going to look at the energy, the potential energy to start with, and the potential energy that we're ending up with. So notice we're starting with about, I would say negative 80, and we're going to negative 300. So the potential energy that we started with was about negative 80. So we put that for that answer. So again, the question was, what is the number of kilojoules stored in the bonds of the reactants? We're going to say about negative 80 kilojoules. Remember, we're calling it negative because of the fact that it's an amount stored. It's not an amount that's being expressed as heat. All right, it eventually will be, but not yet. Number 6 says how much energy is stored in the bonds of the activated complex. So what we'll do is we'll look to see where the activated complex peaks, and it's about 55, something like that. It's a little bit higher than 50, so we're going to say about 55 kilojoules, something like that. So that's the answer to that question. About 55 kilojoules is the amount of energy in the activated complex. Now number 7 says, what is the activation energy for the forward reaction? It's about 135 kilojoules. Let's talk a little bit about how we got there. We started at negative 80. So we take the high, which is 55 kilojoules for the activated complex, and we subtract that negative 80. That brings us to 135 kilojoules. So let's again look at how we got there. We started at negative 80, and we're going up to 55, right? So to get from negative 80 to 0, we have to go, well, about 80, right? And then to get from there to 55, we needed an additional 55. So the difference between those two, about 135 kilojoules. All right, so that's number 7. Let's look at number 8. How much energy is stored in the bonds of the products? So now let's go to the products. We'll go to the extreme right. And if I look across, this is the potential energy of the products. If I look across, I can see that I'm at about minus 300. So that's the number of kilojoules stored in the potential energy, or the potential energy of the product stored in the bonds of the products. So we're going to say about negative 300. So that takes care of number 8. Let's look at number 9. How large is the energy change? We're talking about delta H of this reaction. Is it released or is it absorbed? Remember that the delta H, or the enthalpy change, the delta H is going to be the difference between the reactants and the products, right? Between the reactants and the products. So it's about 220. Let's talk a little bit about how we got there. Remember, we started with negative 80 kilojoules. So negative 80 kilojoules was the amount of potential energy stored in the reactants, negative 80. And we went down to negative 300. That difference between negative 80 and negative 300 is the enthalpy change, delta H. All right? So that's how much energy is going to be released. That's how much energy will be released. Negative 80 minus a minus 300, about 220 kilojoules worth of heat will be released in this exothermic process. Again, products in this process have less kinetic energy than their reactant counterparts, and so this is an exothermic reaction, releasing about 220 kilojoules of heat in the process. Let's go on to number 9. 9 says, sketch and label a dotted line showing how the graph might change if a catalyst were used in this reaction. Let's talk a little bit about what a catalyst is and what a catalyst does. A catalyst speeds up the rate of the reaction and makes the reaction go faster. There are literally thousands and thousands of them in our bodies because without them we could not survive. It's required for energy transfer to happen quickly. So what does a catalyst do? It lowers the energy of activation. That's its function. That's how it works. So initially we started with about negative 80 kilojoules of heat. We ended up with about negative 300. But there was this energy of activation that we had to overcome. Going from here to here required an amount of energy. What a catalyst does, it lowers that energy of activation, making the reaction proceed faster. So what's going to happen is, as we lower the energy of activation, it's going to allow this process to occur much faster. And so that is the action of a catalyst. Okay? So that's what catalysts do. All right. Let's take a look at number 11. What would the reverse reaction, would the reverse reaction be endothermic or exothermic? Justify your choice. Well, in order to understand whether it would be endothermic or exothermic, we have to imagine this curve in the opposite direction with reactants on the product side and products on the reactant side. If that happened, as you can see, the reactants, the new reactants would be higher or lower in energy, lower in energy than the products, right? And so that's what it would look like. In fact, let's make a sketch. On the next question, it asks us to make that sketch. It says, on the axes below, sketch the potential energy diagram of the reverse reaction. So that's what I've done here. Label the axes, potential energy of reactants and products, activated complex, delta H, and activation energy. So I've simply reversed the reactants and the products. We start low now and we go high. Start low and we go high. So this is going to be an endothermic reaction. The reactants are on the left now, the products on the right-hand side. Notice the large energy of activation, because that's the amount of energy that's going to be required to take me from reactants up to the activated complex. Much larger than it would be for an exothermic reaction, right? The delta H, again, is the difference between the reactants and the products, the potential energy of the reactants and the products. And there you have it. That is the endothermic reverse of the exothermic process that we looked at before. That'll do it for this one. I'll see you in the next one. Thanks. Bye-bye.